The next section is titled See How They Run. Yeah. Me too. Rold's an awesome guy. So the question I'm going to ask is pretty simple, and we've talked about it a lot, but why does our band run up? Mm-hmm. It's going from lowest to highest energy. So at k is equal to 0, we've written this out 10 million times already, but what does the wave function look like? Yep, all the basis functions like this. Oops, why did I do that? But now when I look at the orbitals, it's all bonding, right? So we get a sigma bonding. And when we look at pi over a, this case, the basis functions change sign in between. And we get a sigma star.
There goes the door. What the heck is happening?
Whew, caught on its side.
No, it's Christmas. It's Halloween. It's Christmas.
Yeah, it's past Halloween. Now it's Christmas. Forget Thanksgiving. Okay. And as you said, Aiden, we go from low energy to high energy. Low E to high E. But on your daily problem, I asked about px orbitals. So what about if we have a chain, a one-dimensional chain of px orbitals? Mm-hmm. It is backwards. Mm-hmm. Exactly. So now we still have the same mathematical formula. Oops, why? I really want to write 0 there, did I? For k is equal to 0 and k is equal to pi over a. Okay, give you guys a second to scramble that down. Okay, how would I shade these things in? Well, I'm doing it on the right. Did you? Yep. Okay, what about for this one? I shade right. What happens here? Yep. Okay, what type of overlap is this? Yep. Now, the orbitals, are the orbitals in phase with one another? Yeah. Yes, they are in phase with one another, but what type of overlap do they have? Destructive. Here, they're out of phase with one another based upon the math, but what type of overlap do they have? Constructive. So if you've paid attention to my language for a long period of time, even in general chemistry, I try my best not to say in phase and out of phase. This is why. Because when you're in the solid state world, just because the functions are out of phase with one another doesn't mean that they have destructive interference. Here, they're in phase with one another, and they do have destructive interference.
This exact conversation for class about, well, not exact
Yep. That'd be why. Okay, so now let's plot this. Okay, what's my y-axis? Yep, energy. What's my x-axis? Okay, what are my zone limits? Yep, pi over a. Okay, I can't remember if Joe or Aiden said this. How is this thing going to run? Yep. And there we go. It runs down. Opposite of 1s orbitals. Okay, p orbitals, triply degenerate. What other p orbitals do we have besides the px? Yeah, py and pz. What do those ones look like? Next question. What about py and pz? Okay, py and pz, if I had the px, so that would be my px, this is the x direction. What direction do you want to call z? Okay, you want to call z this way? I don't want to do z that way. I want to do z up here, and I want y coming out at us, or in the board, whichever way. So, what's that? No, y was this way. Okay, so we have a set of orbitals that's going to look like this sitting in space. What's the other one going to look like? Yeah. In the plane of the board. The one in the plane of the board is going to suck to draw. I don't want to do that one. So we're going to pick this one. However, what do we know about these two sets? Are they different? Yep, they're both going to be pi-type overlap, and they're degenerate. There's no change with them, especially if it's just things in a 1D line. So, since they are degenerate, meaning they have the same energy, let's just consider just the pz for drawing purposes. Our lattice, again, we'll have these things spaced out. And we're going to call the distance between them A. Okay, let's consider our zone edge and zone center. So again, we consider zone center, zone edge. And when I say zone center and zone edge, what am I really talking about? Yep. So I'm really talking about a specific value of k. If I go to plot those block functions, at 0, what's it look like again? Yeah.
Hi.
Chi?
Plus,
Yeah.
yeah, they're all the same size.
Yep, always the same sign, so on. What about at pi over a?
Alternating.
Yep, we alternate signs. Okay. Let's plot those out. What color do we want to use for our orbitals?
Blue.
Blue? Okay.
We always used to choose blue last semester.
Yeah. Okay, if I fill this one, the bottom first, how do I fill in my second orbital? Same. Hasn't switched signs. Nope. What about for the third one? Yep. Now, I fill in the bottom one at pi over a. Which should the next one be? Top, yep. Next one? Yep. Okay, what type of overlap is this going to be? Yep, this one's pi. What's this guy? Yep. Okay. So this one's anti-bonding, this one's bonding. Everybody feel okay with that? Okay. Wow. Bad. Yep.
Yeah, that happens to me all the time.
Same here. Luckily, it's not been while they've been holding a child, but oh yeah, we went trick-or-treating. I dressed up like Tiny Diamond from Trolls, so I had a shiny shoe here up. It's a costume. I got to wear my glasses. It felt great. Scarlett went as Queen Poppy. Lydia went as Viva, her sister from the third movie. And then my wife went as Queen Barb, the queen of the rock trolls. We're a troll family. It was awesome.
I did not know there's a third troll.
Oh, dude, you got to get in deep trolls lore.
Yeah, it's nuts.
I only know the first one with the jellyfish and the monkey.
No, there's just the three.
The cloud reminds me of you so much. It's awesome.
What?
It's not a bad thing. I think the cloud's one of the best characters. I am Cloud. Not the weepy Cloud from Final Fantasy VII, but okay. We're going to plot all the p orbitals now. Y-axis is E. What's our x-axis?
It is K.
Yep, it's K. Where are we going to go from? Yep. Okay, we already explained the px. How's the px going to be drawn? Below. And what type of overlap was that? It was sigma. Okay. We have to draw the py and the pz. But we need to do it in relation to this px, which is going to have a greater band dispersion. Yes, you're right. Why is px going to have a greater band dispersion?
Higher quality overlap.
Yep. So if you look at the overlap this way, there's like direct contact. However, we always draw p orbitals like this, and then we draw that thing. So inherently, sigma orbitals have better quality of overlap compared to pi. And if you look at instances where you look at the average bond association energy for a carbon single bond to a double bond to a triple bond, it doesn't go double a single bond, double a triple bond, like that way. There's a change there because the quality of overlap is just not as good as a sigma bond. Ooh. Good timing. Okay, so now we need to draw the PZ and the PY with a worse band dispersion, and how do they run? Yep, low to high, and we're going to squish them. Okay, there's my PZ.
It starts at a higher energy than.
Yep, because that dispersion's the center. If you were to average the center, they should be at approximately the same center because when they start as atomic orbitals, they're degenerate. But now, where I've drawn two orbitals, two bands, where's my PY? Yes, overlapped completely. I'm going to put and PY. They're overlapped with one another. So now that becomes somewhat confusing. Let's say we want to look at a system, I don't know, actually, I'm going to leave that as a daily problem. I think that'll be fun. I want you to consider, let's say we have a 1DH chain, or a 1D chain of one of these elements. How are you going to fill in that Fermi level? That's what I want you to think about. And that's what your next daily problem will be.
And is sigma going to have, like sigma as in the 1s orbital, going to have greater band dispersion, just shift it relative, it's going to be lower on this energy spectrum?
Yes.
So the gap between them, it like just kind of comes, the top of band comes closer.
So you like have that.
Exactly. Okay.
Yep. We're talking about like a 2S, and these are the two P's. Okay, are there any other questions right now? Okay.
Wait, you said any of these elements?
Any of the P block first row elements. Like, so I might pick, I'm going to probably pick boron. Actually, no, I'm going to probably pick beryllium, and I'm going to pick like oxygen just to screw with you guys.
I don't know, I feel like boron.
Okay. Actually, boron, yeah, maybe I'll do boron. Maybe I'll do 3. Okay. What I want you guys to be able to do, though, is to do this from the whole thought process. I don't want you just to memorize this because the situation's going to change and you'll have to rationalize stuff. Okay, next time we're going to look at if we have a 1D chain of square planar complexes that contain platinum, and we're going to have to worry about d orbitals. And then we're going to move on to the densities of states and those other bonding things I talked about. Okay?